today's class we will be talking about ordered dictionaries, and we are also going to be looking at binary search trees, which is perhaps one of the simplest ways of implementing an ordered dictionary. So what is an ordered dictionary? So it's essentially that you have the dictionary functionality, right? So recall dictionary was that you have key element pairs, yeah, and you use the key to insert an element, to search for an element, or to delete an element. Besides that, in an ordered dictionary, you have the notion of the minimum, the element with the minimum key, the element with the maximum key, and the notion of a predecessor and a successor, right? Okay, so when I say minimum key, what then it means is that there is some kind of a total order on the keys, right? This is different from when we had talked about hashing. When we talked about dictionary, if you recall, we had said that the only operation that we will ever need to do on the keys is to compare two keys for equality. Given two keys, we have to decide whether they are the same or not. So here we are going to be expecting more out of our keys. Here we are going to assume that there is some kind of an ordering relation on the keys, so that given two keys, I can either decide whether they are equal, and if they are not equal, then I can say one is less than the other or one is larger than the other. Yeah, so there is an ordering relation on the keys. What are the parameters you are saying to the function's predecessor and successor? I have just shown S as the ordered dictionary as one of the parameters. It need not be. Yes. Yeah. So in particular, you could think of the predecessor as taking only one parameter, which is the particular key. So predecessor of K would mean give me the key which precedes K in the total order, in the dictionary S. Right. So dictionary S में कुछ keys होंगी, there will be certain keys in dictionary S, right? So give me the one which precedes the key K and which lies in this dictionary.
This key is like the element on which the entire dictionary is ordered.
Exactly. So keys are the particular field or the part of data on which the things are ordered, right? So there is a total order on the keys. So similarly, the successor function. So what is one way you can implement such an ordered dictionary? So there are two trivial ways of doing it. We are in both cases, let's say, using a list kind of a data structure. So an unordered list would just keep all the elements in here. So all I've shown here are the keys. Yeah. So since it is unordered, inserting takes only a constant amount of time. Searching will take order n time in the worst case, because there's no order, so I might have to go through the entire list before I find out where the element is. And deletion, how much time will deletion take here? Order n, because first we have to search for the element that we are trying to delete. Yeah. How much time would successor take here? Order n, not order 1. Because suppose I say what is the successor of 12 in this dictionary? The successor of 12 is not 22, it is 14, right? Which is the key following 12 in the order relation. So the order relation I'm assuming is just the order on the integers. Yeah. So 12 is the smallest key, 14 is the key larger than that, 18, 22 and 34. So 34 is the largest key in here. Yeah. So given 12, so from 12 I'll have to, given the key 12, I'll have to run through this entire thing to find out the one which was the smallest key larger than 12. Yeah. So both successor and predecessor and min and max will all take order n time. So fairly inefficient implementation. An ordered list, on the other hand, let's say we ordered the thing according to the total order on the keys, right? So now minimum takes only constant time. Maximum also we can organize it so that it takes constant time. Let's say I have a pointer or a reference to the end node in this list. Yeah. Successor also takes constant time, because given a particular node, I can just go to the next one and that will give me the successor. And let's say predecessor also takes a constant time. Yeah, of course. So it depends upon how you are given the node. When I ask for successor of a node, if you have to first search for the node, then of course it will take order n time, because you might have to go through this entire list to reach that node. Yeah. But if I tell you where the node is, I give you, let's say, a reference to this particular node in this list, then you can compute the successor and the predecessor in constant time. right? Inserting also takes order n time, because first you have to find out where to insert, क्योंकि ये ordered है, right? You have to find out the correct position for insertion. Okay, searching takes order n time, because again we have to maybe run through the entire thing. If we use an array, searching can improve, right? And we've seen an example we've seen how to do this. We use binary search to do that, right? So if you put the elements, they are ordered, put them in an array, then we can do binary search to find the element in logarithmic time, log n time, right? But binary search karne se, if we do binary search, then now insertion and deletion still take order n time, right? While we can find out what is the right place to insert an element, we'll have to shift all the elements to the right. Yeah, so it takes a lot of time to do insertion. Similarly for deletion, we know where the element is which we are trying to delete, but then we have to shift everything to the left. Yeah, everyone follows this? Okay, so this is just, I had just to recap what binary search was. So you remember binary search, to search for 22 you would go to the middle element, 22 is larger, you'll go to the right, 25 it's smaller, you'll go to the left, and so on and on. And in that manner you will eventually end up with the array location which has 22, or an array location which does not have 22. In each case you will be able to say whether 22 is there or not there, and the number of comparisons you would take in this process is only logarithmic, because, well, at each point you make every time you make a comparison, the size of the array in which you are making the search halves, and so you the number of time you can halve n to get down to 1 is only log of n, and so you will take order log n time to do the searching. As you recall, insertion and deletion I said will take order n time. Any questions till this point? So this was the trivial ways you would adopt to implement a ordered dictionary, right? But we are not here to talk about triviality, so we are going to look at something more interesting, right? And that's called a binary search tree. Right? So what is a binary search tree? A binary search tree is a binary tree which has a search property on it, right? Recall, what is a binary tree? A binary tree is a tree in which every node has at most 2 children, right? A node can have 1 child, 2 child, or no children. No children means it is a leaf node. And now there is a search property that we are talking about. So each node is going to contain a key and an element. In most of the following, in the discussion that follows, we will not be talking about the element at all. We are just interested in the keys. So what is shown here, written on the nodes, are the keys, right? Now what is the binary search property? The binary search property says the following: all the keys which are less than 5 will be in the left subtree. All keys which are larger than 5 will be in the right subtree. And this property holds at every node, not just at the root node. यहाँ पे भी left subtree में वो keys होंगी जो 3 से कम है. Right subtree will have keys which are larger than 3. Not all keys which are larger than 3, of course there are keys larger than 3 which are here, but basically if I look at the left subtree, all the keys in the left subtree will be less than this node, all the keys in the right subtree will be larger than this node. Similarly for this tree, all the keys in the right subtree, as you can see, are larger than this key value. All the keys in the left subtree, there is no left subtree, so nothing to talk about here. If I look at this node, all keys in the left subtree are less than 7, all keys in the right subtree are larger than 7. Right? This is called the search property. A binary tree in which the nodes have keys which satisfy the search property, so that the search property is satisfied, is called a binary search tree. Okay? Is that clear? So binary tree plus search property equals binary search tree. So if I have these set of keys 2, 3, 5, 5, 7, 8, then I can, so this is a binary search tree with these keys in it. This is also another binary search tree with this same set of keys. So you can have many different kinds of trees with the same set of keys. Both of them are binary search trees because they both are binary and satisfy the search property.
There is an equal to part, like the left subtree should contain a less than or equal to. Equal to part, is it in the definition or it is in implementation based?
It is implementation, right? So keys stored at nodes in the left subtree of V are less than or equal to K. Now you have to somewhere put, okay, so there are a couple of issues here. Here I am assuming that you might have keys which are also two keys which are the same, right? So quite often, so this doesn't happen very often. So quite often you would be using dictionaries only in settings where the keys are unique, right? An element has a unique key. No two keys are the same. But suppose you had the setting where two keys could be the same, right? Can happen, right? Suppose your key was your name of a student, right? You can define a total order on names, let's say the lexicographic order or alphabetical order, and then two names could be the same. So you could have settings in which keys are the two keys are the same. Now then we have to put then we have to decide whether if a key is equal, whether it should go to the left subtree or should go to the right subtree, and we can decide one way or the other. Let's say we say to the left. We could easily have said it goes to the right. Yeah, so there is no problem with that. Here actually I am permitting it to go both ways. It could either go to the left or it could go to the right. Any problem? So don't, okay, so for the rest of the discussion, let me just assume that the keys are unique, right? Otherwise it unnecessarily complicates matters. So we'll just assume keys are unique, do the entire discussion and see if there is a need of duplicate keys, what should we do there, right? If there are duplicate keys, how do we handle that? Now suppose you want to search in a binary search tree, right? Given a particular key, so after all it's a dictionary, we are implementing a dictionary. So given a particular key, I want to find out where the element is. Okay, so let me first show you an example. Suppose I want to search, this is my tree and I want to search for 11, right? So I come to the root, I compare 11 to the key sitting here, which is 5, right? 11 is larger than 5. So a search property says that 11 has to be in the right subtree. Yeah, that was the search property. Keys which are larger than here will be in the right, keys which are smaller will be in the left. So we go to the right subtree and यहाँ पे 11 से इसको compare करते हैं. ये this 11 is larger than 10. So once again, if it is there at all in the tree, it has to be in the right subtree. And so we go to the right subtree. And we go to the right subtree and we compare 11 with this and we find 11 here. So we are done. We have found 11. Yes? So that's what is being said here. To find an element with a key k in a tree T, this is the tree, you are given a key k, so you will compare k with the root, with the key in the root. If k is less than the key in the root, then you will search for the key in the left subtree. Otherwise, you will search for k in the right subtree. Okay? Suppose we have the same example, but now we are searching for 6. So we come here, 6 is larger, so we go right, okay. Then we compare 6 to 10, 6 with 10, 6 is smaller, so we go left. Then we compare 6 with 7, 6 is smaller, so we try to go left, but the left child is null, so it's not there. Because if it were there, it has to be here. It has to be in the right subtree of this guy because 6 is larger than 5. It has to be in the left subtree of this guy because it's less than 10. It has to be in the left subtree of 7 since it is less than 7. So if 6 were there, it had to be here, and since it is not here, it's not there. Any question?
So 6 could have been on the right side of the 5 of the left subtree.
Sorry, let's see. What are you trying to say? Oh. Just one second. What's your question? No question. Okay, good. So we can write the binary search the search procedure in a binary search tree either as a recursive procedure or as an iterative procedure, right. So, the recursive procedure is perhaps simpler to understand. So, you are searching for a key k in a tree T, right. So, you look at the root of T, let us say that is x. If x equals nil, which means there is no root or it is an empty tree, then you are essentially saying that nothing is there. So, just forget this for now. If the key in this node x, in this root node x is equal to the one you are searching for, then you just return this root node. If it is less than the key in the root node, if k is less than the key in the root node, then you have to recursively search in the left subtree. So, you are searching in the left subtree of x, and what are you searching for? You are still searching for k. Yes.
Sir, in the prior version when we are using left, we are using in search the tree, we are putting tree in the search. In the iterative procedure, we are putting only the root node. I mean, when we are changing it, then x is equal to left of x in the iterative procedure. That gives, that assigns the key of the left node to x, right? In the iterative procedure,
Okay, what is left of x doing? Okay, this is all pseudocode, so please don't try to. Okay, so left of x. So let me come to what your question is. X is a reference to a particular node, right? So x to begin with refers to the root of the tree, and then left of x is a reference to the left subtree now, to the root of the left subtree, right? So it's referring to that, and we are searching for k in there. Okay, so that's what we have to do, and if key is larger than the key in the root, then we have to search for k in the right subtree. Okay, this is clear with everyone? Okay, good. Let's go to the iterative version now. In the iterative version, we are not going to make recursive calls to the search procedure. What we are going to do is we are just going to, as we were doing in the search, we are just going to keep marching down the same tree. Right? So we start with x referring to the root of the tree. Well, if x is nil, which means that it's an empty tree, and k is not the key in the root, then we'll do something. What will we do? If k is less than the key, then we have to go left, right? So x now becomes the left child. So x now gets the value of the left child of this current node.
So that means left is defined differently.
Separate definition for it.
Left is defined differently in both of these procedures.
Is it defined differently?
So because one
So
thing
the
is giving the
previous
left
one it
tree, and
gives a
second
subtree.
time it is one time it is giving the reference
Child.
to the left tree,
Right.
and the other time it is giving the reference to the
Left child.
node.
It is
Left node.
Child.
Left child.
See, pseudocode.
Okay, yeah, maybe. Right, so we started off with x referring to this guy, and then we said if k, so suppose there is a key k1 here, we are searching for the key k. If k is less than k1, then we go left. If k is more than k1, we go right. Yeah, and since we go left here, we are now continuing the search here. So x gets a new value, which is either x dot left child, either you want to call it this way, right, or actually in the code that I showed you just now, I had written it as x gets left x, right. Pseudocode, I can use any one of this, right. So this is what it gets to, and we continue the search. So we are basically, so maybe at the next step we go right, and so on and on till we reach here. This is where our node is. So x will keep getting modified. So it will, first it's pointing to this node, then it's pointing to this node, then it's pointing to this node, and eventually it's pointing to this node, right. It will keep getting modified in this manner. Right. How much time does search take? Right. So So let's look at the iterative version of the search. Right. So what we did was that with each time we went through this while loop, which is right here, we came down one level in the tree. We went from a node to one of its child nodes, either the left child of that node or to the right child of that node. So एक level नीचे आ गए, we came down one level, right? So we started at level 0, which is the root. Then we came, after one run of this while loop, we came to level 1. After that, we came to level 2, level 3, and so on. So how many times will we execute this while loop? The maximum number of levels in the tree. And what is the maximum number of levels in a tree? It's the height of the tree, right? So the height, if the height of the tree is h, then the running time of this procedure is no more than h. So order h is the running time of this procedure. Everyone understands this? Right? Simple. Okay. Now h, recall, can be very large. Right? I might have a tree on n nodes whose height is order n. Yes, and we'll see in what kind of a situation this happens. But note that the height of the tree could be very large. The search time is only order h, the height of the tree, but the height of the tree in particular can be as large as the number of nodes in the tree. Let's look at another procedure, that of finding the minimum element in the tree. Right? Where do you think is the minimum element in a binary search tree?
Bottom leftmost.
Why leftmost leaf? Leftmost leaf? Leftmost leaf? Leftmost node or leftmost leaf?
Leaf.
Leftmost leaf.
Yes.
Okay, let's see why that is wrong. Suppose I have a tree which looks like the following. Okay, I need to put in some keys so that this looks like a binary search tree. So let's put in 7, 5, 6, 12, 13, 11, 10. This is a binary search tree? Yeah? Okay. Now, which is the smallest node here? The leftmost leaf. Okay, I do not know what leftmost leaf means, but well, this might be the leftmost leaf, but this is not the smallest node. Yeah? Smallest node is 5. So it's really the leftmost node, except leftmost node also doesn't make too much sense.
Last
Right?
leaf having the
Last leaf. This is not a leaf at all.
last node having a left node. Who's left pointed? Me.
Right, so let's not try to say which node.
So
The
the
last
leftmost
internal node.
What is the last?
What is
So it is
the
the
last
leftmost node.
internal node? Victor?
It is the
This is
leftmost
an
node.
internal node. You want me to create more internal nodes without left children? No. Right? I can create more internal nodes without left children. So this is also an internal node without any left child, but this is not. So yeah, don't try to give half a sentence definition of which the smallest is, but let's give a procedural definition, right? So which is, how do you find the smallest? Start at the top, keep going left till left becomes null. Yeah, that is clear to everyone. There is no doubt on that. Yeah, so start from the top, keep going left till the left is null, and that's the smallest node. How about maximum?
Start on the right.
Keep going right till the right becomes null. What's the proof? Why is this the minimum?
Because everything to its right will be better.
Something on the right, it's the number is greater than that.
Right. So the proof is very simple. The minimum has to be to the left of this root, right? So it has to be in this subtree. Right? So in this, yeah, then now you have smaller subtree, so you can just apply induction or use it. Right? So the smallest has to be left. Now there is nothing to the left, so this has to be the smallest. Everything to the right has to be larger than this. Yeah. So in one line, that's a proof for this fact. Okay. So that's the entire code essentially. You want to find the minimum in a tree x. So while the left of x is not null, just do x is left of x. Keep going left, left, left. When you will stop, when left of x is null, at that point you will just return x, or return the key in x, or return the element, or whatever you want to return. Yeah. So how much time do you take again in this? Is this clear, or you're reading it from here? Yeah. So why? Because the same argument. With every run of this while loop, we are going down one step. So we can go down at most the number of the height of the tree, and so that's the maximum time we'll take. So the same procedure can be used with small modification to compute the maximum, right? We just have to replace the left by right, and then we'll compute the maximum. Okay, let's see how to compute the successor element of a tree. Successor, understand what successor means? Successor means given a particular key, I have to find out the next one. So given x, find the node with the smallest key greater than key of x. Right चले जाएंगे? Okay, let's see. So there are two cases. So आप लोग सब कह रहे हैं, all of you are saying कि right subtree में जाके निकाल लेंगे minimum. So two cases क्या होंगे कि right subtree है या right subtree नहीं है. अगर right subtree नहीं है तब भी तो successor हो सकता है tree में. नहीं हो सकता. So there are two cases really, right? So case one is when the right subtree of x is non-empty. There is something in the right subtree, right? So the picture is हमारा, this is the node जिसका हमें successor निकालना है. Right subtree is non-empty. There is a right subtree, right? It exists here. तब हमें क्या करना होगा? So then we know that the key which is larger than this, right? All the keys in here are larger than this. We know that. But why should the successor be lying here? Why can't the successor be somewhere else? It is greater than this.
If it is an internal node and it's not on the right, then it can be on the top one. If it left में अगर tree का close है, it can be on the bottom. In this case, it has to be.
Why should the, okay, so this is not completely clear to me, right? So, okay, I know that the keys here are larger than 5, right? But there are other keys which are larger than 5, which are, yeah, the parent is one key which is larger than 5.
Yeah, it can be.
What can be?
So the parent and the right subkeys in the parent can be the, it may contain the successor.
अगर 8 नहीं होता तो 10 will be the successor of 7.
Right, so lots of confusion here, right? So we need to look at it more carefully. Let's look at it more carefully. Okay, so what are we trying to say? So let me draw this picture that was there on a fresh sheet of paper. So I have 5. Let me draw it again. I'll put down 5 here in the center, and we have 10 here, we have 7 here, and we have 8 here. We have 1, 1, 3. Now I have to find out the successor of this gentleman, 5. I am trying to find out the successor of this node. This has a right subtree. Now all of you are tempted to say that the successor of this guy has to lie in this right subtree. You want to say that the successor lies here. Why? This is not the entire tree. Please remember, there could be, it could have parent. Yeah, it could have a parent. The parent is going to be larger than this guy.
It has to be larger than everything.
It has to be
It has to be
larger
larger
than
than everything in that tree. Everything.
The parent is larger than 5. When
larger than
when is it larger than 5?
When it's in the left subtree.
When?
Five
When
is
it is in the left subtree, right? So there are two possibilities. The parent is larger than 5, which means it's in the left 5 is in the left subtree of the parent. But then this guy will be larger than all of these guys, because all of these guys then are in the left subtree of the parent. So ये successor नहीं हो सकता. This parent can then not be the successor, right?
We refer to parent only when this guy, right? We are
When you don't have right.
is not having a right.
Why? That is the procedure which you have learnt. But why? So why is it that the successor only has to be in this right subtree but nowhere else if the right subtree is not null?
So you want the minimum which is greater than 5.
Fine?
You want the minimum element which is greater than 5.
Yeah.
And so everything to the right of the 5's parent will be larger than 5.
Right. But the next element which is larger than 5 could be, let's say this is my entire tree, it could be somewhere here, right? Why not?
Every element will be more than
Every element will be more than this.
On the right will be maximum of all the entire tree, and all the elements right to it will be greater than that. So it cannot lie in unless this is null. The right of 5 is null.
Right. So let's say, so the easiest way to think of this is as follows. Suppose we were searching for some element slightly larger than 5, right? We were searching for the successor of 5, right? The claim is that we would, how should we say, suppose we were searching for 5, the claim is that we will end up at this node. That's the point, right? That whatever decisions we are making the decision and we would end up at this node. Yeah. Now, if the key we were searching for slightly larger than 5, then that means that, or we are searching for the successor of 5, then that means that once again we would end up at this node and proceed right. Yeah, because it's larger than 5. So which means that any successor of 5 really has to lie in this part of the tree. So in this part of the tree, the successor is essentially the minimum node, because all the keys here are larger than 5. Yeah. So the minimum key here is the one we are looking for, and we've already seen a procedure for computing the minimum, which is that keep going left. Yeah. So we'll go left, and we can't go left any further. So this becomes the successor of 5. Yeah. So this reminds me of the remote I have at home. Great. Okay, so that's what we have to do. If the right subtree is non-empty, then we go right one step and keep going left. Right. The other case is when the right subtree is empty. So suppose I was trying to look for the successor of 3. Right. If I am trying to look for the successor of 3, the right subtree is empty. So where is the successor of 3 now?
Check for the parent.
Look at the parent. Look over the upper level till you have a right node, but till it is the left subtree.
Right. So the procedure is the following, and we'll see why it's the right procedure. What you're going to do is start going from from this node to its parent and then to its grandparent and so on, till you reach a node such that this key, this x that whose successor you're looking for, is in the left subtree of that node. So you went up to here, but note that this is in the right subtree of this node. Then you went to its parent, and here you found that 3 is in the left subtree of 5. Right? So you'll stop here, and this becomes the successor. So you understand the procedure, but why is this procedure correct?
Because
We go to the right.
on the right of this parent, we'll be having the numbers greater than this.
So once again, recall the procedure. The procedure is I am searching for the successor of this node. The right subtree is null. There is nothing to the right. Then I go to its parent, and I go to its parent, and I keep going up to the parent till I reach an ancestor such that this node, whose successor we are trying to find, is in the left subtree of the ancestor. Yeah. So this guy then is going to be the successor of x. This node is going to be the successor of this. Why is this true?
So because the predecessor of that one will
Everything
be
is less than.
What?
All this we are
Yeah. So this node has to be. Is it larger than this? No, it is smaller because it's in the right subtree. So it is smaller. This is also smaller. This is also smaller. This is larger.
larger than the
entire lot, entire left.
So larger than the last one.
In fact, this guy is in the largest node in this entire subtree. Yes, because how did I find the largest node? I come here and I keep going right, so which is exactly what I do, right? So this is the largest in this entire subtree. Yeah, and the node following this is then this guy. Yes or no?
Yes.
Right. Can the successor could have been somewhere else? Could it have been to the right of this guy?
Because the right hand will be
Because all of these are going to be larger than
Yeah,
this. Can it be an ancestor of this guy?
that will also be greater than.
This ancestor
Greater than that.
is less than this.
Greater than.
But this
It is greater
ancestor,
than-
if it is less than this, it is also less than the entire thing. So it's not a successor of this. But if we were looking at this ancestor,
Then it would be greater than the.
then this ancestor is
would be lesser. So it would be lesser
Sorry.
than the number.
Reverse.
this ancestor would be less than this, and it would be less than the entire thing. So I was wrong. So this ancestor is less than the entire thing. So it's not really a successor, but this ancestor is greater than this entire thing, but it is also greater than this. So this is only the successor.
What we're saying is answer.
Yeah. So bit of a confusion, but you understand what the arguments are.
Okay, so कौन सा top में?
Topmost.
Question?
जो हम कह रहे हैं answer.
Question?
उसका से
No question. Okay. So I'm going to continue with the so let's see what code I can write down for computing the successor. Right. So if the right is not null, then I just return the minimum in the right subtree. Right. And if the right is so, otherwise I'll come to this point. So I'm looking at the parent now. So y is the parent, and what am I doing here? If y is not null and x equals right of y. So when do I have to keep marching? Till x becomes the left, right? So essentially I am recall I am going up the tree. So I am going up the tree, and the first time I essentially I am at a node such that the parent is such that the node is the left child of the parent. Then I stop. Yeah, the first time. So let me show you the previous slide. The first time, so I keep going up here. The first time I come to a node such that the parent such that this node is a left child of the parent. Then I stop. So for instance, if I were looking for the successor of 8, I would go up like this and this. This is the first time the node is a parent or is a left child of its parent, and so I stop it here. So that's what we are doing here. So initially y is parent of x, and so all we are doing is we are moving the pointers x and y, right? So y is parent of x, and then we are changing it so that x takes the value y and y takes the value of parent of y. right, so that it moves one step ahead, right. So in some sense these are a pair of pointers which are moving up the tree with y always ahead of x, x, y, right, and then x moves and then y moves and then x moves and then y moves and so on, right. And then when do we stop? When x is the one which is trailing, y is the one which is ahead, when x is a left child of y, right, when x is a left child of y, then we stop. So essentially we are continuing in the loop till x is a right child of y. When x becomes a left child of y, we will get out of the loop, or y becomes null, that means I have gone beyond the root, then we stop and we return, right, we return y, which was the parent node.
We have to return to that it is not found.
Right. In case y hits null, then we will return y, which means null. If we return null, which means it was not found. Yeah. So you can have a closer look at this code and convince yourself that it is correct, but this is. So once again, what's the running time of the successor code? Order h. In each of the cases, in one case what we are doing, we are going down the tree, but we can only go down as many levels as the height of the tree at most. In the other case, we are going up the tree. So the maximum number of levels we can go up the tree is at most the height of the tree. Yeah, everyone with me? So now let's look at the insertion procedure in a binary search tree. So till now we have looked at search. How much time did search take? Order h, height of the tree. We looked at minimum, we looked at maximum, both of them take time proportional to the height of the tree, worst case time. And successor, we looked at successor, successor took time proportional to the height of the tree. Can you also compute predecessor? Similar idea, right? Essentially interchange role of right and left. सक्सेसर में जो भी हम काम राइट में कर रहे थे वो अब हम लेफ्ट में करेंगे, वही काम नहीं, सॉरी, पहले हम अगर राइट चाइल्ड नल नहीं है तो हम राइट चाइल्ड में मिनिमम निकाल रहे थे, अब अगर प्रीडेसेसर में अगर लेफ्ट चाइल्ड नल नहीं है तो उसमें हम मैक्सिमम निकालेंगे, ठीक है, एंड वी विल मार्च अप द ट्री एंड ऑल ऑफ दैट द सेम थिंग. एनी क्वेश्चंस? समथिंग इज sounding fishy, not convincing? No. Good. So let's look at insertion, right? So that's the other thing we'll do today, and deletion we will take care of deletion in the next class. Right? So insertion, I have a binary search tree and I want to insert a certain element. So what should I do? I'll first search for the element, right? I first find out the place in the tree where the element should be. Right? We are assuming distinct keys, right? We are assuming that no two elements are the same key. So we find out first where it should be, and then we put it there so that it is actually there. So let's look at an example. This is my binary search tree, right? And I'm trying to insert 8. So pehle, if you recall, this 8 was not there in the tree. So I first search for 8, which means I go down, I come here, go right, I go left, and then I want to go right, but right is null, which means 8 is not in the tree. 8 is not in the tree, so I put 8 right here, which means that 8 becomes a right child of 7.
So basically the point where the search fails, we inserted there.
Exactly. So wherever at whichever point the search fails, because we hit a null pointer, a null reference, we put the node there. That's all insertion does. Okay? Everyone with me? Good. How much time does insertion take then? Order h? Yeah? So it's the same as searching. Essentially आपने search किया, उसके बाद जो है एक pointer एक reference को change कर दिया और वो आपका insert हो गया node. Straightforward. So now that brings me to that question that I had asked at the beginning of the class, which is in what order should I be inserting the keys in a binary search tree so that its height, so we said the maximum height of a binary search tree is n or n minus 1 or one of those things.
Ascending or descending, if it is, and we take
Right.
the
So, so this is the maximum height of a binary search tree. Right. Suppose I have n keys. In what order should I insert those keys so that I get a tree of height n minus 1?
ascending or descending.
Right. So, let us say our keys were 1, 2, 3 up to n. So, what order should I insert them? Exactly this order or the descending order. So, 1 जो है हमने पहले किया, 2 जो है हमारा इसके बाद यहाँ पे आया, राइट, 3 जो है इसके बाद आएगा, राइट. अंडरस्टैंड यहाँ ऐसे क्यों आ रहा है, राइट. 4 के लिए हम यहाँ आएंगे, राइट जाएंगे, राइट जाएंगे, राइट जाएंगे, यहाँ पे हमारा जो है नल आएगा तो हम 4 यहाँ पे इंसर्ट करेंगे. वी विल इंसर्ट 4 एट दिस प्लेस, and in this manner we will create a chain of this kind and we will get a tree of height n minus 1. Right. Similar would happen if I had inserted in the descending order. So, which order should I insert it in so that it gets a small height? Huh? So, first element I should insert is n by 2. Okay. Which is the next element I should insert? N by 2 minus 1? N by 4. Nothing. And 3n by 4. Right, then I would get something like this. And now n by 8 and so is it clear that n by 8 will come here? It's clear to everyone, right? Why? Because we'll compare and we'll put it here. And which is the next one? 3n by 8. Suppose I insert 7n by 8. If I insert 7n by 8, what happens? So, can I insert 7n by 8 at this point? Can I insert 7n by 8? No harm, right? I can also insert it here. 7n by 8 will always come here. Right? Now I can insert my 3n by 8, which is what you were. And now I have to insert 5n by 8, which will come here. Essentially, I have to go level by level. Or I have to insert these nodes first and only then do I have to insert the later nodes otherwise. So, in this manner, I will end up creating what kind of a tree?
Height balanced.
Height balanced, a complete binary tree. I have not told you what height balanced trees are. You don't know what a height balanced tree is. You don't even know what a full binary tree is. We have only learnt what a complete binary tree. So, this we will get is a complete binary tree. Complete binary tree provided your n was some power of a 2 or 2 to the k minus 1. Yeah, n has to be of the kind 2 to the k minus 1. Right? Then you will get a complete binary tree. Okay. So, in the next class we are going to ask ourselves the following question. If I were to take a random permutation of these elements, right? If I put the elements in an ascending order, then I get a bad tree. Why am I calling this a bad tree and this a good tree?
Height is minimum for this.
Height, because of the height. This has a huge height, this has a small height, right? Why is height so relevant? Because all our operations were dependent upon the height of the tree, right? The smaller the height of the tree, the faster the operation is. So, we would like to keep the tree height as small as possible. Yeah. So, we don't really want trees of this kind. Yeah. Of course, with some effort you could figure out in what order should I insert these elements so that I get a small height tree, and what is a bad order. Right. Suppose I were to just take a random permutation of 1 through n. Yeah, you understand a random permutation? Take one of the permutations, there are n factorial different permutations, take one of them at random and insert elements in that order. Right. What will be the height of the tree then? Depends on what?
The permutation.
On you or on me? Who does the insertion?
On the permutation.
On the permutation, right? It will depend upon the permutation. So, we have to talk of a random variable, right? You have to talk of, so the height of the tree will now become a random variable. You understand what a random variable means? A variable which takes many different values. So the height of the tree could take one of many different values. What are the many different values that the height of the tree can take? Log n to n. Yeah? Log n to n minus 1 or log n plus 1 to n minus 1. I don't know exactly which, but one of those, right? Log n to n. So it will take one of these different values, and it will take each of these values with a certain probability, right? Because after all, I took a random permutation. And so, what have we to find out? So it's taking each of these values with a different probability. So we have to find out what the expected value of this random variable is. Yes? Okay. So we'll address this kind of a question in the next class. Any questions on what we did? We will take this after, take it up after this class. Yeah. Any other questions on what we have done today? So this can be the code for insertion. So I'm given a tree T. वहाँ नहीं आ रहा है. I'll just switch. This can be the code for insertion. I am trying to insert this node Z into a tree T, right? And once again, I'm going to have 2 pointers X and Y. And what is the need for these 2 pointers X and Y? Because recall that when I'm inserting a node, so when I'm inserting this node Z, I'm searching for Z, the key corresponding to Z in the tree. And then I hit this null, right? And so we said we'll put Z at that place. But to put Z at that place, what will you have to modify? The parent of Z. उसका right child आपको modify, right child या left child आपको modify करना होगा. उसके contents modify करने होंगे. तो आपको essentially parent के अब तक pointer रहना चाहिए. तो हम अब क्या करेंगे? We'll have 2 pointers X and Y, such that now the game is that Y will be preceding X. So these 2 pointers will keep moving down, right? Such that Y will always be the parent of X. Right? So that's what we are doing. Initially Y is null, X is the root. Then Y takes the value X, and X goes to either the left or the right child of X. And we keep doing this till we hit null, till X becomes null. When X becomes null, Y is pointing to the right node. अब Y का हमें left या right child change करना है. So Y is going to be the parent of the new node we are inserting. So parent pointer of Z. So recall that the nodes also have a left child and right child and the parent. So parent of Z gets the value Y. And well, depending upon whether the key of Z is less than the key of Y or more than the key of Y, if key of Z is less than the key of Y, then Z will be a left child of Y. Then the left child of Y becomes Z, and if key of Z is more than the key of Y, then the right child of Y becomes Z. That's all you have to do. But does everyone understand what the need for having these 2 references is, right? You need to keep track of the parent because that's the one you have to modify. Yeah? So you'll go modify that and you'll just set it appropriately to the left or the right. So we are, okay, so I already discussed this. So in what sequence should insertions be done? And we saw that it should be this kind of a sequence. So with that, we are going to stop our discussion on binary search trees. We'll continue this in the next class with the deletion procedure for binary search trees, and we'll also look at this question that I asked you today, that if you were to insert elements in a random order, then what is the time taken to do the insertion, and what kind of a tree do you get as a result of that then. Okay.